Welcome to your first lesson in college physics. That's right, this is college physics and not AP physics. The reason I make the distinction, I am teaching you in preparation for what you're going to be facing in your first quarter or first semester at any university. So, my name's Ryan. You will address me as such. Any questions, feel free to ask them whenever you want. You can post in the comment section down below. You can also just shoot me an email if you already have my email address. Okay, so the first thing I want to start with is, what is physics? What do we know about it? Well, I could easily have sat there and told you that physics is everything, and that's generally true. Almost everything that we interact with, all the motion between two objects, the friction that we experience, the reason cars are able to move along the surface of the planet, planets orbiting around the sun, satellites orbiting around the planet Earth, the way that moon controls the tide, forces of gravity, forces of electromagnetism, all of these things are physics. But at its core, what does it mean to study physics? What does it mean to become a physicist? And it took me a while, even while I was at UCLA, to grasp onto what that concept was and what it truly meant. So to me, I've narrowed it down to a few things. Physics is like being a detective. So congratulations, you are now Sherlock Holmes. The idea here is that you're solving problems. There's a question you ask and you're solving the problem behind that question. You're creating different questions. The second thing, congratulations, you've just graduated from Hogwarts School of Witchcraft and Wizardry. That means you can do magic. So what I mean by magic, there's certain things that we do as physicists. We play with the numbers, we dwindle them down to their simplest forms and just get rough approximations. We find clever ways to work through our derivatives and integrals that make life so much simpler. So we become mathematicians, essentially. Most of your math teachers will get a kick out of you saying that, or most of them will have made that joke by now. But that's really what it is at its core. It's just harmonious between all subjects of not only science and mathematics. That's what the beauty of physics is. It combines both in such a way that you actually begin to not only feel smaller, but you change your perspective on things. And the last thing, you become an expert in losing sleep. Now, this last one is more of a point that you're going to be noticing a lot when you get into college. You're going to be staying up pretty late studying, doing your homework, meeting with classmates, doing all sorts of things just to prepare yourself and get ready for what's to come. Now, all of this is to say, and not only to add a little bit of humor for you, but all of this is just to tell you that your journey through physics is to prove to you that you know nothing. Okay, what do I mean by you know nothing? Well, what if I told you that even though it's going to be about 100 degrees outside today and it's really hot and we're sweating bullets and we need to go inside, chill out in the AC, we need to jump in our pools, we need to, just stay away from the heat that we're just melting from outside. What if I told you that the most important thing that I ever learned in my time at UCLA was that the universe is always cold? What do I mean by that? Well, let's take a simple example. Let's say I have this box here, and it's a nice, bright, and sunny day. I'll use the rainbow marker because why not? Nice, bright, and sunny day. And it's about, I don't know, 100 degrees Fahrenheit. Now, yes, I know I'm using Fahrenheit and not Celsius. Guess what? This is not chemistry. And even when we're going to be using temperature, we're not going to be using Celsius either. We're going to typically be using Kelvin, but hey, this is mechanics. We don't care about temperature just yet. So let's say it's 100 degrees Fahrenheit outside and the sun's beams are beating down on this box. If it were truly hot, this box would melt and change from a solid to a liquid state. Note the importance of that statement. You go from a solid to a liquid if it's truly hot enough. Yet, our houses are still solid. We go outside and we're not liquid form. Yeah, we're sweating a lot. That's just our body maintaining homeostasis. But we're still solid. We're still tangible. We can still feel everything. Bricks still exist. Metal still exists. Why is that? The answer is because the universe is freezing cold. You can only have a solid piece of matter if the universe is cold. It took me until my senior year at UCLA, when I took a solid state physics class, to really understand what that meant. I had a professor constantly coming in wearing a huge parka or a snow jacket. He would just show up very first lecture, a few lectures later, wearing this big jacket, and it was the middle of our spring quarter. So it was already pretty hot, especially in May. And so we're all looking at him questioning, why are you wearing that? Then he tells us, because it's freezing outside. And he went in to explain why. And that's exactly what physics has shown me, that I understand so little, yet grasp so much more than I ever could possibly imagine. Now, we've covered what physics is. We've covered 3 very important things that you need to learn and already accept as a physicist. But we haven't gone into the nitty-gritty details of what I expect from you and what most universities are going to expect you to be able to do. The first thing, you're going to have to get used to using no calculator. And I'll put no calculator because you're going to need calculus. So, by needing no calculator, that means you're going to be having to manipulate numbers as much as you can to be able to think quickly and move through different calculations at a rapid pace. So much so that math becomes second nature to you, essentially. The second thing, you need to be good at working with equations. Forgive my shorthand, EQNs stands for equations. So when we're talking about working or manipulating equations, that means you're working with some formula and deriving everything that you need, going from one place to the other, always maintaining, oh, I know what this comes from, or I know what to do with this. Truly, you can do this using dimensional analysis. And what dimensional analysis is, you're analyzing the units to make sure that they all add up to the final unit that you're supposed to get. Things like joules, things like newtons, all of those are units, and you need to make sure all the math you're doing leads you to those units for your end result, depending on the question. But although it's useful to work with the units, it's also really useful to know how to manipulate the equations and all your variables just to get things down to a very small, concise form. Now, what I mean by that is you're going to go from something really complex, like say, oh, I don't know, F equals KQ1 Q2 over R squared. This is Coulomb's law. I believe there's a negative in front, but I'm going to ignore it for now. So let's say I have this expression. I should know how to manipulate this to then get the electric field equation, which should be negative KQ1 Q2 over R. I need to know how to do those things. Now, both of these things are completely related to one another. They just have different units and different meanings attached to them. But we should know that taking the integral of this force expression with respect to my radius r yields my electric field expression. And it's important that we understand how to work with these things and go back and forth, because really what it does for us, it allows us to memorize far less equations. You memorize maybe one or two of them, and you have the rest of them at your disposal. Plus, it's really important that you see the connections in every single theory. So there's connections between kinematics and energy. There's connections between energy and work, between work and forces, between forces and so many other different things that you're going to be encountering as you progress through physics. Even things like gravitation, Newton's universal law of gravitation. There's a correlation between how that connects to classical mechanics. And I'll get into what's called Lagrangian mechanics, which is far more advanced stuff, but I'll do that just as a bit of a freebie for you so that you can see, oh, they are actually related to one another. Now, to start off with, we're going to have a bit of a math primer. And you'll see this in the lecture notes that I'll go ahead and make sure you have access to. Either through a Google Doc that I'll make sure you have a link to in the description down below, or through a PDF, or just email me and I can send you the PDF copy of those lecture notes as well. So, for your math primer, there's a few things that you need to be aware of. You should already know your quadratic formula. Which, this doesn't just mean x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. It doesn't just mean that formula. It really just means you should know how to work with quadratic equations. You should know how to complete the square. And really, those two things, the quadratic formula and complete the square, are exactly the same thing. You should know how to factor expressions. You should know how to FOIL things out to then cancel out different terms, or solve for the zeros and find the intercepts, which is really the same exact thing. You should know how to do those things. That's just from your Algebra 1 course and a little bit from your Algebra 2. You should have a firm understanding of linear functions. So, slope-intercept form, what the meaning of the slope is. It's not just rise over run. Most people will always ask you, what is the slope? And they'll say, oh, it's rise over run. Although that's true, the actual definition of what the slope is the amount of change in one object over the change in another. It is the rate of change of your function. So that's a good definition that I want you to pay attention to. Slope is the rate of change. And this is going to be really important when you start getting into your calculus material, because the derivative is defined to be the rate of change of a function. But the rate of change of a function is the function's slope as it climbs along a curve, as it moves along a path. That's exactly what you're doing in physics every single step of the way. Notice, math and physics, they're the happy couple. And that's sort of a joke that I like having with you guys. Math and physics are the father and mother, or mother and father, however you want to phrase it. But they're the parents. And their children are things like chemistry and biology. And unfortunately, I always make this joke, and I'm sorry to any biologists or anybody who studies biology in any way, but biology is the kind of the runt of the litter. We think we know they're important, and they're great, and we love what they do. But the scope of the math that they have to do isn't necessarily to the same level that it would be in something like chemistry. And you're going to notice that when you get into your first few classes over at UCLA or in any other university, when you're taking your first year life science courses. It's a lot of memorization, hardly any math. If you have any math, it's usually statistics in there, but it's rare that you're going to have to do any calculations. A lot of it is just memorization and regurgitation of the information. Whereas in chemistry, you have a lot more equations that you have to deal with. Although chemistry uses a lot more algebra. You're not really deriving too much, especially in your first year for chemistry, but it's useful to know where things come from and how they're all connected to one another. So if you feel the need or feel so inclined to derive an expression in chemistry, by all means. Nothing ever should be, I guess, in your head keeping you in this state of disillusionment where you think it's not possible to derive an expression. You can always get something from another equation. The next thing you're going to need to know, and I really hope that your teachers at school would have gone over this, but don't worry, I'm going to record a few lectures and we're going to go over this very slowly. But you should know derivatives. I know my R looks like a V over here, whatever. You should know derivatives, which again, this is a calc-based course, so this is a calc-based portion of the course. And we'll get into the definition of the derivative. You should also know your trig functions. And this is also not limited to, but exponentials. And by exponentials, I'm referring to logarithmic functions, so like natural log. And again, we're not going to be calling it natural log, ln. We're going to be calling it log. Now, when you get into college, the natural log becomes log. It is not log base 10. Natural log is log base e, but they refer to it as log. So whenever you hear them say log, it's always referring to ln. The reason being, it's the easiest one to work with because its base is always going to be a constant, no matter what you do. And we'll get into exponentials and how to work with the change of base formula to show you where this is all coming from. Now, as far as your trig functions are concerned, you should know your sine, cosine, tangent, and all of their reciprocated forms. You should know your trig identities, so like the Pythagorean identity and how to get the other three or the other two from them. You should know your double angle formulas, very useful, especially more so when we're getting into harmonics, which isn't until much later on anyways. You should have some foundation as to how they correspond to the equations of a circle. When we get into circular motion, that's when these things start to really rear their ugly heads. Things that you don't really want to pay attention to or really don't think about. They show up. The next thing, you're going to need to know a little linear algebra. Not a whole lot. It's just pretty useful to really understand how things correlate. Now, this isn't necessarily part of the first year physics course at UCLA. Might be elsewhere, but not too big at UCLA. It's also not very big or emphasized in the AP course. But I throw it in here because it really helps, especially when you're discussing the right-hand rule, to show how the cross product of something is its curl and how it rotates based off of which directions that things are going. All based off of how the other three fingers, your middle ring finger and pinky finger, bend with respect to the other two axes directions. It's really quite fascinating how that actually plays out, and it took me forever to understand and see the correlation between those things. Now, there's got to be a few more math things that will come up throughout the course. For example, I may require you to know how to do integrals. We'll go over that in case you don't know it, which stands for the area under a curve. Or the antiderivative. Now, basically what that means is you're going from your derivative backwards. Now, when it also comes to the trig functions that I mentioned right here, you're going to probably find this expression very useful. But Euler's equation, or Euler's formula. It's going to be really useful in certain cases, and it might help you in your calc courses as well. And it's just a useful tool because it's really easy to integrate with respect to exponentials as opposed to trigonometric functions. But nevertheless, I'll go ahead and teach it to you. This isn't required for you to know either, but it's just useful. And remember, the things in quotations are not required, just useful. The other thing And this is not limited to calculus, to math of any kind, or anything specific. But the most important thing I want you to know for any subject, any topic, anything that we cover throughout this course, anything that we cover throughout any course, and whether it's history, whether it's English, whether it's math, science, art, music, whatever the hell it is, always remember, ask questions. It's really hard and really difficult to be that student that raises their hand, puts themselves out there on the line, and doesn't ask the question or asks questions. Really, it's really hard to ask the questions that need to be asked. There is no such no such thing as a bad question or a stupid question, unless you're in a physics class asking, "When was the Peace of Westphalia signed?" Or you're sitting, "What about the Peace of Utrecht?" And you're in a math class. That doesn't make too much sense. And it's not that it's a stupid question, you're just genuinely curious, but you're asking it in the wrong place. So, ask questions. You'll get answers. Most of the time, your question is exactly the same question as someone else. They're just not brave enough to ask that question. So be willing to ask the questions that you're afraid to ask. Okay. So, what I'd like to get into, I'm going to assume you know this. I'm going to assume you know slope-intercept form. I will probably start here with derivatives. I'm going to get into Euler's equation. And I'll show you some exponentials. But there is one thing that's pretty important when it comes to the linear or the quadratic formula that I want to make sure we address before we get into the other stuff. So let's go ahead and start there. Quadratic formula. So you know it to be x equals negative b plus or minus square root b squared minus 4ac. And then divide that by a factor of 2a. Okay, this comes from ax squared plus bx plus c equals to 0. Now, a, b, and c are just undetermined constants. They're undefined constants at this point. They could be positive or negative. Technically, it could even be imaginary. But we're going to just focus on the fact that they can be positive or negative at this time. Now, it's great. You know this is something that you're going to be working with and you're going to be seeing all the time. But what if I told you that this formula, this quadratic formula, has a direct connection to complete the square? So I'm going to take my generalized formula here, and I'm going to convert it using complete the square. And I'll show you that it's the same process. So as you know, with complete the square, you have to subtract the c term. Let's go ahead and do that. Next, I have the preference where I like to get rid of my leading coefficient, that a. So I'm going to divide everything by a here. So divide that by a, divide that by a. That was not supposed to happen. Undo, undo. Okay, divide that by a, and divide that last one by a. The next thing, which I will write in blue, you take your second term, divide it by 2, square it, and add it to both sides. So we'll do that in green. So we have parenthesis here, b over 2a quantity squared. Now I'm going to reveal something about this expression on this left-hand side in a second. So then this is going to be b squared over 2a, or well, let me get rid of that squared on the inside right there. We're going to have b over 2a quantity squared on the outside here, minus c over a. Okay, this portion right here. So once you divided your second term by 2, squared it, and added it to both sides, it just so happens that that term, this middle term right here that you divided by 2, is going to be your factor term, always. So pay attention to your signs. Here are all pluses. So we're going to have x plus b over 2a, quantity squared. This will always be the factoring, is equal to, now let's go ahead and distribute this square. So we'll have b squared over 4a squared minus c over a. Now, what I need to do is multiply this right term by 4a over 4a. Gotta have common denominators in order to solve for this expression. So hopefully by now you're starting to get an idea of what this will look like. Let's go with this rainbow color. Ooh. Okay, so x plus b over 2a quantity squared is equal to b squared minus 4ac all over 4a squared. Next thing, take the square root of both expressions. Notice that 4a squared is going to become my 2a up here in the quadratic formula. So let's go back to black. X plus b over 2a is equal to, remember the square root always gains a plus or a minus, b squared minus 4ac over 2a. And look at that. I subtract my b over 2a right here. Negative b plus or minus the square root of b squared minus 4ac all over 2a. So, complete the square is just a rather expanded way of doing your quadratic formula. It's useful in certain scenarios because it makes things a lot easier, but they're exactly the same formula. They're directly connected to one another. Pretty cool. Something that I figured out while I was tutoring one day. Decided to look at it carefully and play with it, and well, yeah, I got bored. Anyways, yeah. Moving on from our quadratic formulas. Feel free to pause this video whenever you want and see fit. I'm going to try to keep the lectures around about 45 minutes to 50 minutes, just like they would be a first-year UCLA class. Most first-year lectures for physics are going to be about an hour long. Never an hour 15, never an hour and a half. Always about an hour. Okay. The next thing. So we've gone over our quadratics. We need to go over derivatives. We need to cover your trig functions. We need to cover Euler's equation. And we need to make sure you know how to work with your exponentials. Now, the most interesting thing I can probably show you how to work with before your trigonometric functions is probably the exponentials. So let's go ahead and cover that just really fast. Let's say I've got a term like 2 to the x is equal to 8. Now, yes, obviously, you can go ahead and solve this saying that 2 to the x is equal to 2 cubed. The base number is 2. The exponent x must be 3. Hey, look at that. You solved it without using logarithms. But let's say that you had to use a logarithm, that was the task that you had at hand. So this top portion right here is a good way for you to check your solution and make sure that you're doing it the right way. But let's use logarithms. Now, most of you would have probably used log base 2 because, well, these are base 2 numbers, so why not? I'm going to go ahead and dissuade you from doing that. We're going to go ahead and use the natural log of e, and I will show you why by using the log of 2. So let's say I take the log base 2 of my 2 to the x, and I set that equal to log base 2 of my 8. Okay. Now, in order for me to make sure that these two may have the same base numbers or even just convert them for any particular reason, we have to do what's called a change of base formula. So let's say I've got something that's like x times log base b of a. And I'm trying to solve for what log base b of a is. Well, if b and a don't have the same base number, let's say that in here I have 3 and I have log base 2 right here, that could be really annoying. Because I could easily have written this as x times log base 2 of 3 is equal to log base 2 of 8. Sure, this one on the right side has a solution, but the left one doesn't, which makes it a little bit more difficult. So the change of base formula is the following. You take the log with your new base, and I'm going to say it's e, of the larger number right here, the a, divided by log base e of your original base number b. This is the change of base formula for that log portion. So you'll have x out here in front because you're multiplying it with that term. Again, whenever you're dealing with logarithms, the exponent attached always comes out front because it's the term that you're searching for. Logarithms help you find the exponent or solve for the exponent because they're exponential growth functions or exponential decay functions. Your first exposure to logarithms is usually in Algebra 2. Sometimes you'll have faced it early on in chemistry, especially when you're dealing with pH and POH. You're going to see log a lot. And that's log base 10 for chemistry. You don't see natural log all too much unless you're dealing with half-life, which is in radioactive decay. And that's something that I went ahead and, teach most of my chem students, or I teach most chem students when I was working as a teacher. You need to know natural log. But wait a minute, I have log base e here. What is that? Well, if you have log base e, you have the log with respect to a constant. So what this actually becomes, log base e is actually the natural log. So that means I could have used the natural log of 2 and the natural log of 8. Granted, 2 and 8, really easy to work with. Obviously, we did it in a much easier way. But if you're required to do this, then you would take the natural log of 8 divided by the natural log of 2. Then you know that 8 is 2 cubed. You bring out the 3. Natural log of 2 over natural log of 2 is just 1. And then you just wind up with x equals 3. So problem solved. Everybody's happy. We can move on. But this is the connection between the natural log and log base 10, or log base e in this case. All right. Your next bit of math. So, hopefully for your trig functions, you've already learned about SOHCAHTOA. And most of the time, I would always say that that's probably the most useful thing that you can expose yourself to, where sine is the opposite over hypotenuse, cosine is the adjacent over hypotenuse, and tangent is the opposite over adjacent. Fantastic, wonderful, great. Let's toss it. Let's start with the equation of a circle. And I'm going to center this circle around the origin, but let's go ahead and just give you the generalized formula. X minus h squared plus y minus k quantity squared is equal to your radius squared. Okay, so now I am saying that the center h comma k of your circle is at the origin, so 0 comma 0. Meaning this expression is much easier to look at because it's now x squared plus y squared equals r squared. Kind of looks like this guy, doesn't it? And in fact, this is where they come from. The Pythagorean theorem for right triangles only exists because it works when it's contained within a circle. Even if it's not contained within the circle, it still works, technically. It's just your circle then gets a bigger radius every single time. So none of the stuff that you've been covering is ever different from one another. They just call it a different name and tell you that it's different. But you've seen it before. It's all the same stuff. They're trying to make you think it's impossible, but it's not. Now, x squared plus y squared is equal to r squared. Okay. Well, what if I then drew a triangle or some circle? So here's my circle. It's ugly, it's lovely. Oh, hey, it made itself pretty. And I'm going to go ahead and put my radius right there. That means this radius has some x distance and some y distance. So there's my y and there's my x. And look at that, we made a right angle right there. So what does that then tell us? Well, let's try to focus in here on this angle theta, right there on the inside. I'll go ahead and just draw that out there with an arrow. Theta, the symbol or Greek letter for any angle. You can use theta, you can use phi. I will redraw my phi because I think it's not so, no. I can do this. No. There we go. So you could have phi. Eventually, well, when you get to higher level courses, you'll be using psi. You might even be accustomed to using things like x. You might be accustomed to using y. You can literally use any variable that you want. But typically, we're going to be using theta. Eventually, you can even use omega. But we're going to be using omega later on in this class for something else. So, theta is the angle that we're going to be using. Now, we know sine of your angle theta to be the opposite side from the angle over the hypotenuse. In this case, our opposite side is y, and our hypotenuse is r. So this tells me that instead of saying opposite over hypotenuse or adjacent over this and blah, 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 what we're actually saying is that sine of theta is y over r. It really becomes so useful to designate these things with respect to the axes that they correlate to. Now, this is going to be a little bit muddied up when you start getting into forces and Newton's laws, as well as when you're drawing your free body diagrams, because at certain times it looks like the sine of your angle applies to the x-axis. But that's just because of the axis of rotation and which way your perspective is turned. So it's not that it changes its meaning, it's on a different axis. It's not the end of the world. The next thing is that cosine of theta is x over r. Okay, so how am I going to relate this back to the equation of a circle? Well, you know your Pythagorean identity to this point, I hope. And that tells me that sine squared theta plus cosine of squared theta should be equivalent to 1. Always. By definition. If you have any different angle theta, then, like say I have cosine squared of 2 theta plus sine squared theta. That ain't going to work. But if I have cosine theta and sine theta, and they're the same angle theta, and I square them, and I add them together, I will always get a value of 1. This works for the unit circle. Okay, this is the unit circle. Unit referring to 1. It's a circle whose value, or whose radius has a value of 1. Remember that. The unit circle is a circle of radius 1. Okay? So, I'm going to go ahead and square my sine and cosine functions. So that means I'm going to get y squared over r squared plus x squared over r squared equal to 1. Now, I hate having fractions. I think they're disgusting. I think they're gross. Not really, but you know what I mean. I just like things to be pretty and all on one line. So I'm going to multiply everything in this expression by r squared. So r squared times 1 becomes r squared. R squared cancels out with r squared here. R squared cancels out with r squared there. Now, although my order is different, x squared plus y squared equals r squared, remember that addition is commutative. It is not associative. So the order here doesn't matter when you're adding x and y squared together. So that's the new definition that I want you to adopt for sine, cosine, and that includes tangent, which you know tangent to be sine over cosine. But I want you to adopt y over x as it corresponds to the axes they are staring at. Now, it's really important, and I'll go ahead and assign this probably as your first homework assignment, that you take a look and practice what your unit circle value is. So you should be able to know what the sine of a value pi over 2 is versus the sine or cosine of the value pi over 3, let's say. You should know that the sine of pi over 2 is 1. You should know that the cosine of pi over 3 referring to 60 degrees, is 1/2. You should know these things. Hopefully you math courses, you actually got around to covering what the unit circle is, and actually that you covered that these angles are in radians, because you will be using radians quite a bit, or degrees, but make sure you know how to go from one to the other. And we'll go over a few examples of that. That way you're prepped for the homework assignment that I'll be giving to you. But know what the radians are, know what these values are. Your first worksheet is going to be on the unit circle. So I'm going to focus on that. Probably not going to get into derivatives until maybe the next lecture because I've got about 10 minutes left in this one. Okay. So let's go ahead and cover more about the unit circle. So for your unit circle, you're going to be getting a worksheet with a giant circle, grid through it, and then all these X and Y blanks along specific angles. You're going to have to label the angles and yada, yada, yada. You're going to have to go through the chart and make sure that you understand what each one is. Let's go ahead and show you how to convert from radians to degrees. That's the first thing you're going to learn how to do. And vice versa. So radians to degrees, and I'm going to use the equilibrium symbol that you should have learned about in chemistry. That is a forward arrow followed by a subsequent backward arrow to degrees. So to go from radians to degrees, or degrees to radians, let's say I have a measure of 90 degrees as my angle. Well, in order to convert, I simply multiply this by pi over 180 degrees. The degrees will cancel out because technically degrees and radians are unitless. They're just values or units that we've associated to an angle, just so we have some sort of distinction. So you have 90 divided by 180, which is 9 over 18, which is just 1/2. All that's left over is your pi term, meaning that this is pi over 2 radians, or pi over 2 rad. And to go backwards, let's say I have a measure of pi over 6. You simply reciprocate your factor. So you multiply it by 180 over pi. The pi's cancel. 180 divided by 6 is then going to give me 30 degrees for my angle. That's how you go from one to the other. You need to make sure that for each of the angles that you're working with, you know how to do that. You should also not use a calculator while doing these conversions at all. I don't want you to use a calculator. Don't do it. It's going to hurt you. Learn how to do it using your head. Learn how to do it using basic math tricks. Second thing, if I give you the cosine of an angle, you should start to see the pattern, especially on the unit circle, of what happens when you move along from one axis to the other. So if I have the cosine of 0, I'm going to use radians. So 0 radians is a value. I should understand and know full well that the cosine of 0 is when x, or the x-axis, is at its maximum. The reason for this, on your grid, cosine of 0 is right here. Do you have any y values there at this point? No, you don't. And I'll go ahead and redraw that point in red so you can see it. You don't have any y values at that point. You only have x as a maximum. And cosine and sine can only equate to 1 as a maximum unless you have an increase in amplitude. We're going to worry about that later on. So, cosine of 0, because x is a maximum and because cosine can only have a value of 1, cosine of 0 is automatically 1. Therefore, what is the sine of this angle theta? 0. Well, we don't have any y values. If there's no y values, that means it has no value, meaning it is 0. Okay? You'll notice that as you move along the grid, where 1 was a maximum, it becomes a minimum. So the cosine of 90 degrees is going to equal 0. Make sure you put the degree symbol in there. That looks like an 8. I'm going to redo that for you. So you should know, ooh, don't like that. You should know that the cosine of 90 degrees is equal to 0. Notice how when you move 90 degrees or you shifted it 90 degrees or by one rotation counterclockwise, not clockwise, counterclockwise, cosine and sine switch places in terms of their value. The same could be said for the sine of 90 degrees. It switches places and it becomes the maximum, equating to 1. So you're going to go through the chart that I'll provide to you in an email. You're going to fill out that chart. You're going to solve for each one of those things. That's your very first little piece of homework. We're going to go into more math stuff and make sure that you're all brushed up and ready for what may come. because I'm also going to give you some trig manipulations to make sure that you can do those just fine as well. Now, let's go ahead and use these last 5 minutes to preview the last bit of information you're going to need. Or at least what I think is a very important bit of information. The derivative. And yes, I know I'm skipping quite far ahead and getting into derivatives before I get into vectors. And we'll get into vectors and what they are and their meaning. But that'll be for the next lecture. This is just your math primer of things you need to know before we get into physics. And vectors all over physics. So, a derivative. First thing to note about a derivative. What it is it is the rate of change of a function. Now, that could be a big change, which is where we use capital deltas. So delta f over delta x. It could be a small change where we use lowercase delta d. It looks like just a regular d. So we get have df dx. The bottom value, the dx or delta x, is what you're taking your rate of change with respect to. What that means is if I have a function f of x, I am deriving that with respect to all the x variables in that function, not to any f's, because there is no other f's inside of that function. You could also see this as partials. Now, the partial derivative is, again, when you're dealing with multivariable calculus and higher order things. I also think it looks pretty because it's like a backward 6. But you can use, you'll see any one of these deltas at any given point in time. In your first year physics courses, it's unlikely that you'll see the partial, but it's good to know. So, what do we mean by its rate of change? Well, you have this thing called the limit definition of the derivative. And what the limit definition is, it's the maximum value that it approaches at a certain point. Now, what we are trying to do with the limit definition is eliminate the variable. So, the way that it's going to work, you will have some function f of x. And again, this is a function with respect to x. This is not f times x, this is f of x. Get used to that algebraic notation. And we are going to take the limit of this function as it approaches a value x minus h or x plus h. Truthfully, shouldn't really matter, but it's going to just say f of x. I think it's, I'm going to just double check this real quick. Give me a second. It's plus h. Yep. I had a feeling it would be. So you're going to take it as it approaches some x plus h value away from your x. This is usually a finite distance or a finite amount, a very small change to the function, but it also could be a large change as we've seen with the capital deltas. It doesn't really matter. So what this then looks like is the following. You take the limit as h approaches 0 of f of x plus h, because that's the bigger value, minus f of x all over h. The goal here, whenever you're doing these functions or whenever you're working with this particular limit, is to cancel out the h in the denominator, because anything over 0 is undefined. But we know that the derivative can't necessarily be undefined depending on what you're working with. Now, that isn't to say that you can't possibly have an undefined derivative. It's completely possible. If I'm taking the derivative with respect to a variable that doesn't exist, then, well, there's no derivative. It would be 0, if anything. But we'll get into that, and don't worry, we'll show you. So, let's say I'm dealing with a very, very simple function, x squared. And I am going to take the derivative of this function using the limit definition of the derivative. So, that means I'm going to take the limit as h goes to 0 of f of x plus h. That means wherever I see an x, I replace it with an x plus h. Minus the original function, x squared, all over h. So I'm going to go ahead and make this our last little example that we're going to go over. Going to go over the time a little bit. My apologies. And you need to write this limit portion every single time. Make sure that you do that in your calculus courses. You will lose points, or you might not receive credit if you don't do it. That's also like writing dx at the close of every integral that you write. You'll lose points if you don't do it. You have to close every integral with a dx, or you could even put it in the front if you're a physicist, but don't do it in your math classes. They'll hate you for it. We'll get into that later. Anyways, so x squared plus 2xh plus h squared minus x squared all over h. Notice the original function, x squared and x squared cancel out, so that's gone. We have h, h, and h. I'm going to get rid of one h. So this leaves me with a function that leads to, or that reads, the limit as h approaches 0 of 2x plus h. Now I can go ahead and plug in 0 for h. If I have the limit of a function without the variable, like I do with the 2x here, then the limit is just this function, because that's technically a constant. So we'll have 2x plus 0. I've already plugged in the h value for my limit, so 2x plus 0 then gives me 2x. Therefore, 3 dots like this in a triangle means therefore, the derivative df dx, also known as f prime of x, that is prime notation, is equivalent to 2x. That means the derivative of x squared is 2x. Always. We'll go into practicing this a bit more, and you'll see how other derivatives work, but we'll save that for next time. All right. Have a good one.